Hello everyone, welcome back to this course again. So today we are at lecture 7 and we shall continue where we left last time, which is about gallium nitride and polarization. For lecture 7 and lecture 8 we will discuss about GaN and also discuss the context of high electron mobility transistor and also briefly get a feel for how the 2D electron gas is formed vis-a-vis the polarization that is there. Okay. And then this week is the second week, and so lecture 9 and 10, which is the last two lectures, which are the last two lectures of this week, we will talk about Schottky multipliers and varactors. Okay. So over to the whiteboard here. So if you remember, we are talking about gallium nitride and its alloys. Okay. And the unique property that they have is polarization, which we did introduce in the last lecture, and this polarization is a very unique property which allows you to which gives you another degree of freedom to essentially tailor the properties of the heterostructure so that you can get better device performance. Okay. You have to remember that gallium nitride is a band gap of 3.4 electron volts, so that is a wide band gap. Okay. And although its alloys can go from 0.7 electron volt to 6.1 electron volt, but for most practical purposes for the RF devices we typically talk about AlGaN-GaN heterostructures, okay, or ALN GaN for instance, indium aluminum nitride GaN, which means the band gaps are pretty large. All these materials and the barrier, this forms the barrier, they have a band gap which is much larger than the gallium nitride band gap. Okay. And these are all gallium polar orientation. Remember we talked about gallium polar. Okay. So now if you recall from the last lecture we had introduced the concept of polarization and how the polarization forms. Okay. So polarization in a way is charge basically. So if you have a slab of gallium nitride, okay, there are many unit cells here, okay, and so at each unit cell there is a negative charge at the top and positive charge at the bottom, and that arises because of the fact that the overall the bonds are polar. So if you take the gallium nitride tetrahedra, okay, this is suppose gallium, this is nitrogen, nitrogen, nitrogen. So you have these polar bonds where there is a partial negative charge at nitrogen, partial positive charge at gallium, and the total out of plane dipole or the polarization does not vanish. It is a non-vanishing charge that appears, and it is not a mobile electron or hole charge, it is not an ionized impurity charge, it is like a dipole that gives negative and that gives positive. In plane it vanishes. Okay. That is why this is polar, and there are two factors. One is that the electronegativity difference between the atoms, okay, and the second is that the crystal is a distorted woodsite. Distorted woodsite is basically like a hexagon, a distorted hexagon, sorry, it is a distorted hexagon which is called woodsite. Okay. Woodsite structure is a distorted hexagon, and because of these two reasons you have this net polarization appearing in the vertical direction, and okay, it is a non-vanishing basically polarization that appears, and it lacks inversion symmetry. The crystal lacks inversion symmetry, which means if you flip it upside down it does not have the same identical polarization. If you flip it upside down, the top will have positive and the bottom will have negative, which we call gallium nitride, which is nitrogen polar. Okay. Gallium nitride which is nitrogen polar. So this sheet negative charge at the top, sheet positive charge at the bottom have the same magnitude but opposite sign. We call it say sigma p. For gallium nitride it is about say minus 0.029 coulomb per meter square. Okay. So sigma p for say aluminum nitride it is much higher, minus 0.081 coulomb per meter square, which is almost 3 times close to 3 times higher than that of gallium nitride. Okay. So similarly indium nitride will have minus 0.0232. I am talking this is negative because I am referring to the top charge only. So the bottom will have exactly the same magnitude but opposite sign. Okay. This is about polarization. Now I had told you that also there is something called piezoelectric polarization, and that arises because of the strain in the layer. Okay. Because of strain, these materials are piezoelectric, which means if you apply a mechanical strain then they can induce a charge or voltage and vice versa. So if you for instance have a layer of aluminum gallium nitride, okay, and that you are depositing or growing on top of gallium nitride, then the lattice constant A of aluminum gallium nitride, okay, the lattice constant of the layer aluminum gallium nitride is actually smaller than the lattice constant of the layer of gallium nitride. Okay. What it means is that aluminum nitride is suppose this, then gallium nitride is suppose this. So, which means you have to pull these atoms apart. So, this creates a stress or a tensile stress in the layer of aluminum nitride, and you cannot, therefore, the more thicker you grow, the more stress it accommodates, until at one point aluminum gallium nitride can no longer hold or maintain the energy that is required to keep it strain. So, it will crack. There is a critical thickness D beyond which it will crack. Okay. So, there is a limit to the thickness of aluminum gallium nitride that you can grow. Why do you grow aluminum gallium nitride on gallium nitride? Because only then you get something called a high electron mobility transistor. You need a material which has a wider band gap, and the polarization should be such that you can generate a 2D-dimensional electron gas at the interface, about which we will come very shortly. Okay. So, this strain gives rise to a polarization called sigma pz. Similarly, again the extra polarization is either going to add up with the spontaneous polarization or it is going to subtract. It can be either in the same direction as the spontaneous polarization. The spontaneous polarization always exists. The piezoelectric polarization exists only when there is a strain in the layer. If for some reason the layer is not strained, then the piezoelectric component will not be there. Okay. So, in all these cases the gallium nitride bottom layer is assumed to be very thick. So, it is relaxed. Okay. It is assumed to be very thick, and this is basically, you can think of it as a substrate, although it is not technically the substrate in most cases, but we can think of this as the substrate, and so it is relaxed. So, the layer that you are growing on top is the layer that actually is going to be strained. Okay. Now, this piezoelectric polarization arises because of the strain, and so there is an expression for this piezoelectric. Pz stands for piezoelectric polarization. It has a certain expression mathematically which you do not have to use every day, but if you know the expression it is helpful, and there are certain material properties for different layers that will give you some values, and you need to use those values to calculate this. So, typically there is an Excel sheet or calculator that will, if you tell the substrate, for instance this is gallium nitride and the top is suppose AlGaN. By the way, AlGaN can have different composition of aluminum, say 0.2% aluminum and 0.8% gallium. So, that the aluminum mole fraction is says 20% here. So, that is X, and gallium mole fraction is 1 minus X. So, if you specify X and the substrate below, which is gallium nitride, you can have an Excel sheet with all the equations put up, which will calculate the piezoelectric polarization that you will get and the sign of the polarization, whether it is negative at the top, positive at the bottom. Okay. So, this basically goes as 2 times A minus A naught by A naught. I will come to the expression. Okay. And then E suffix 31 minus E 33 C 13 divided, this is 13, okay, not B, and C 33. Now, this looks very exotic and very bizarre, but essentially what is happening is that A and A naught are the lattice constants of the layers. What is A and what is A naught? A naught actually is the lattice constant of the AlGaN that you are growing. Okay, lattice constant of the AlGaN that you are growing, and A is the lattice constant of the substrate on which you are growing, which is gallium nitride. Sometimes it could be different also, so that is why it is A naught is the lattice constant of the layer that is growing, A is the lattice constant of the substrate on which you are growing the layer. Okay, so that is fine. So, you can see that AlGaN has a lattice constant which is smaller than that of GaN. So, this quantity, maybe I can use a red mark here. So, this quantity is always going to be positive for AlGaN GaN, simply because of the reason that A minus A naught is greater than 0, because the lattice constant of AlGaN is smaller than that of gallium nitride. By the way, these are Woodside, or which is like a distorted hexagon. Okay. So, they have 2 lattice constants actually. Okay. It is good to know that they have 2 lattice constant. Okay. One is this outer plane lattice constant called C, and one is that in plane lattice constant called A. So, we are talking about A here. C is the outer place lattice constant. When A changes, C also will change, but this expression does not have C. Essentially, when you stretch it apart, the C will also shrink or expand, depending on how, if it is pulling apart, if you are pulling it out, then C will reduce. If you are pushing this in, then the C will increase. But we do not keep C in this expression, we only talk about A, because A is the lattice constant in a lateral direction. Now, E31 and E33, what are they, right? What are E31 and E33? So, these are actually something called piezoelectric coefficients. You can say piezoelectric coefficients of the material, which is algan in this case. So, E31 and E33 are piezoelectric coefficient, these come from their material property. This is elastic property, you can say, I mean not elastic, this is piezoelectric property, you can say, because the material is a piezoelectric material. So, there are certain material constants associated with the piezoelectric nature of the material. So, E31 and E33 are piezoelectric coefficient, and you can calculate them if you know the value of x, which is your algan mole fraction. For instance, you will know E31 for ALN and you will know E31 for GAN. So, you use Vegard's law. So, 20% for 20% algan, you will use 0.2 into E31 for ALN plus 0.8 into E31 for GAN. So, this total will give you the E31 value for algan 20%. Okay, these material properties for ALN GAN are known, these are piezoelectric coefficients. And so, what happens is that C13 and C33, these two quantities are called elastic constants. These are elastic properties of the material, of the layer that you are growing, which is algan. Okay, this is elastic constant of the material. So, mechanical property, you know, every material will have some elastic constant. So, this is precisely that elastic constant. Now, these quantities E31 is always negative, okay, while E33 is always positive, okay, and C13 and C33, these are also always positive for woodsite III-nitride, okay, these are always positive. So, you can see that you know E33 is positive, C13, C33 are positive, but E31 is negative, which means this area this term under the bracket is always negative, okay, and this quantity is always positive. So, piezoelectric polarization for algan on GAN with tensile stress, or any material on any other material for III-nitride family with a tensile stress will lead to a net negative will lead to a net negative piezoelectric polarization. When I say net negative piezoelectric polarization, I am talking about the top surface. So, the top will have negative, the bottom will have positive. So, Pz on the top will be negative, Pz on the bottom will be positive. But remember, the spontaneous polarization of algan is also negative on the top and positive at the bottom. So, which means the piezoelectric component and the spontaneous component are in the same direction and they are reinforcing each other. So, piezoelectric polarization of algan, tensile stress on GAN, helps you enhance or improve or increase the strength of the total polarization. Okay. Now, in case of compressive stress, this would have not have been the case. For instance, if you had a layer of in GAN, just I am telling you in GAN on top of GAN, then what would have happened is that in GAN spontaneous polarization will again be negative on the top and positive at the bottom. Okay. In GAN positive at the bottom, negative at the top. However, in GAN has a larger lattice constant than GAN, something like that, whereas GAN has a smaller lattice constant than in GAN, which means you have to squeeze them up, which means your in GAN is actually pushed inward. So, mechanically you can say this is a compressive strain, and because of the compressive strain, you know, the A naught of the in GAN layer growing is actually larger than A of the GAN layer on which you are growing. So, if you recall the last expression 2 A minus A naught by A naught, this quantity becomes negative, okay, because A is smaller than A naught. A naught is in GAN the top layer, A is GAN the bottom layer. So, this is negative. The other term was always negative if you recall. Okay. So, essentially what happens is that piezoelectric polarization for a compressively stressed layer, in this case it is in GAN on GAN. So, it will give you a positive value, which means the top, okay, the top will be positive. So, I can take the blue color here, the piezoelectric polarization will be top, the positive at the top and negative at the bottom. Now, it so happens that for in GAN on GAN, the spontaneous polarization of in GAN on the top, which is negative, is actually much smaller than the piezoelectric component on the top because of in GAN being stressed, which is positive, which means the top surface has a total positive and the bottom surface has a total negative, because the piezoelectric component is too strong, okay, the magnitude is too strong. So, it overwhelms the spontaneous polarization, and this quantity is so strong that it basically dominates the overall polarization. Okay. So, in all this discussion, whether it is in GAN GAN or say for instance algan GAN, when we talk about this different polarization, you know, spontaneous and piezoelectric polarization, we need to keep in mind that the gallium nitride layer, which is though relaxed and therefore has no piezoelectric component, but still has a spontaneous polarization component which is negative at the top, okay, and positive at the bottom, correct. In between there is no polarization, because as I told you, the unit cell, when you pile up on top of another to form the total crystal, this is negative, this is positive, this is negative, this is positive, they all cancel out. Only what remains is the negative on the top and positive at the bottom, rest everything is cancelled out. Now in a case of an InGaN-GaN structure, InGaN-GaN structure, the total polarization because of InGaN, okay, the total polarization because of InGaN is positive on the top, negative at the bottom, okay, and because of GaN is negative at the bottom and positive at the negative at the top and positive at the bottom. This is spontaneous polarization of GaN, this is the net polarization of InGaN. But for LGaN-GaN it is opposite, so this is LGaN and this is GaN, okay. So the piezoelectric polarization is negative, the spontaneous polarization is also negative, piezoelectric polarization is positive, spontaneous is also positive. So the net is positive, the net is negative. Gallium nitride gives a negative here and a positive here. Now given this charge distribution, how does the energy band diagram look like? Because if you can draw the energy band diagram, you basically understand the device problem. Suppose someone tells you that I have proposed the new heterostructure where I have LGaN on top of say ALN. ALN aluminum nitride is relaxed and LGaN is compressively stressed. LGaN is compressively stressed because of the fact that ALN lattice constant is much smaller and LGaN is slightly wider, depending on the composition of LGaN of course. If you have aluminum which is a very high percentage and gallium is low, then you are approaching ALN, but in general say 20 or 30% LGaN, then you will have a larger lattice constant for LGaN. So it is compressively stressed, you are stressing it this way to mimic the crystal structure below. Now will this structure be of this heterostructure be of any use in making an RF device? No. Why? Because you need to understand how the band diagram for this will look like. If you can draw the energy band diagram, which is the conduction band, the valence band and the Fermi level for this entire heterostructure, then you can figure out whether or not this device would or this structure would be useful for making a transistor, any transistor. So that is the energy band diagram, the strength of energy band diagram, and we all need to be able to draw the energy band diagram. To draw the energy band diagram, first you put the charge diagram. Once where are the charge distributed? Once you have the charge, you can integrate the charge to get a field, because the charge is nothing but derivative of the field, correct? Derivative of the field is the charge, and once you have the field you can integrate to get the potential V or potential, because the derivative of the potential is the field, okay, and if you add a minus q there it becomes the energy band. So potential and energy band are essentially mirror image of each other. Potential in the unit is volt, okay, and if the energy band is you charge the charge of the electron, which is negative of the 1.6 into minus 10 to minus 19 coulomb, has to be multiplied to volt. It will give you electron volt, which is equivalent to joule, I mean in dimension I am talking about, its energy basically, okay. 1 electron volt is an energy unit of energy. So electron volt represents the energy band. If you have the potential like that, say V, then energy band will look like that, you know, it is a mirror image, okay, and this is electron volt energy band and potential is V, okay. So this is the trick to basically being able to draw the energy band diagram, alright. So the energy band diagram, how will you draw the energy band diagram now? One second, I am coming to the next slide. So for instance, I took the case of LGaN-GaN, okay, this is LGaN and this is GaN. Now before I draw the energy band diagram, I have to tell you that the layer of gallium nitride is fairly thick, because this is the substrate, or at least it is either the substrate, but in practical cases this is the thick buffer layer, okay, very thick buffer layer. So what happens is that the polarization at the bottom interface, which is this sigma p sp sigma sp, okay, for gallium nitride, it gets basically something called screened out, or it is basically compensated. Essentially what is happening is that this charge, the charge below is too far away, and especially if you are trying to grow it on a foreign substrate, say sapphire or maybe silicon carbide or maybe silicon, these are the substrate on which you try to grow the gallium nitride, then at this interface there will be lot of impurities, lot of nucleation sites, a lot of non-uniformities, etc., those will screen out the effect of the bottom polarization, or you can say that bottommost layer actually is not as smooth or as uniform as the top layer, here you will have a lot of discontinuities, lot of halox, a lot of nucleation layers that form like this. So the bottom layer, the bottom polarization is actually effectively screened out. However, if this layer is not so thick, this is suppose not even like very thick, if it is even few hundred nanometer, and below that you don't have a substrate but you have another layer of say algan, and that algan is suppose grown on substrate, say silicon carbide, then this interface, this bottom interface of gallium nitride, we cannot ignore the, if this interface, this sigma spontaneous polarization of GaN which is positive cannot be ignored, if there is a epitaxial layer below which is say algan, and this is suppose not very thick, you know. If it is also very thick, eventually it may get screened out, but in general we are talking about algan GaN, just algan GaN. So in all practical purposes this layer polarization sigma sp which is positive can be ignored, which means the main components here now of charges are that you have at this interface you have a negative spontaneous polarization of gallium nitride, you have a positive spontaneous polarization of aluminum gallium nitride which is larger in magnitude than that negative of the gallium nitride. Why? Because algan has a higher polarization, plus you have a piezoelectric polarization because of the fact that algan layer is strained, both of this positive is much stronger or larger than this negative here. So the effective is a total positive charge here. Okay. On the top you have similarly minus sigma sp which is the spontaneous polarization of algan minus pz which is the piezoelectric polarization of algan. So the total is negative here. Okay, the total is negative here. However, invariably the top surface of algan will always have things like say dangling bonds. Okay, even if you grow it in vacuum you will eventually get some particulates, moisture, even if you not have moisture, okay, even if you have ultra high vacuum, still there will be some defect states there. Okay, there will be some defect states there, etc. So those are donors, they are like surface, we call them surface donors, they donate electrons, and become positively charged at the top, So they donate electrons, actually those electrons will come and form a channel at this interface. Okay, they will form a channel of electrons at the interface here. Okay, so they have donated the electrons, and so at the surface here there is a sheet of positive Nd plus, I will call it NDD plus, that is a sheet of positive donor ions. This is not polarization by the way, these are fixed immobile donor ions on the surface, we call them surface donors. They also coexist with the negative, total negative polarization charge that is there at the top. Okay. So now given this information, how does the charge diagram look like? So I am drawing all of this so that I can draw the energy band diagram of an algan GaN HEMT. What will I gain if I can draw an energy band diagram of an algan GaN HEMT? If I can draw the energy band diagram of an algan GaN HEMT, then I can actually understand the device, I can actually truly appreciate what the device is doing, and that will help me make a transistor. And if I can help make a transistor, then I will make an RF transistor, not a generic transistor, I will make an RF transistor. Okay. And if I make an RF transistor, what is so special about gallium nitride RF transistor? Of course we have discussed this, it is a wide bandgap material. So the RF power performance that is offered by gallium nitride, okay, the output power that you can get in watt or watt per millimeter is far higher than what you can get in any other rival contemporary technology. So that is the, and so it is very promising and useful, and that is why we are discussing the energy band diagram here. Okay. So if I draw the charge, so I will draw the charge, okay, and x axis is the distance. So if I say this is 0, the top, this is 0, I will go this way x, I will go down. Okay, so the algan thickness is suppose d, and the GaN thickness is very large, I do not care, right. So GaN thickness is very large. So what I do is that at this is d, okay, at d, if you recall the slide before, I have a very high negative charge, okay, I have a very high negative charge at this interface which overwhelms the total positive charge from GaN. Okay. So here I have a huge positive charge, sorry, here I have a huge, at this bottom interface I have a huge positive charge which is much larger than the negative spontaneous polarization charge, not this interface, sorry, this interface, okay, the L-GaN-GaN interface. I have a huge positive charge which comes up because of the positive spontaneous and positive piezoelectric component of polarization of L-GaN, and this is larger than the negative spontaneous polarization of GaN here. So, the net is positive. So, I will call this plus sigma net, and this net is basically sigma sp of L-GaN, okay, plus pz of L-GaN minus sigma sp of GaN. This is L-GaN, okay, that is your net positive. At the top surface at 0, at this surface, I told you there is a significant negative charge there because of the negative polarization. I will call it minus sigma top, and that is basically minus spontaneous polarization of L-GaN minus piezoelectric polarization of L-GaN, that is the total negative charge. So, there is a negative charge here, there is a positive charge here, and also I told you that there is a surface donor charge here plus q and dd because they have donated charge. Now, the total thing becomes charge neutral if there is a negative charge here, we call it q and s. This q and the total is now charge neutral. This q and s is a sheet of mobile electrons, okay. This is a sheet of mobile electrons that forms to basically balance the charge, you can say it forms to basically balance the charge. The total charge is now neutral at equilibrium, and this forms at this interface, at the L-GaN-GaN interface, but slightly towards GaN, maybe a couple of nanometer towards GaN, okay. And this charge that forms is called a 2-dimensional electron gas, okay. It is called a 2-dimensional electron gas. We will come to that very soon why, alright. And the total charge neutrality is maintained now. So, I can write down the charge neutrality, okay. I can write down the charge neutrality as here q and dd plus, right, plus sigma net is equal to q and s plus, I am only considering the magnitude, okay, sigma at the top. This is basically negative, but I am considering the positive, so it is equal basically, alright. So, this is the charge neutrality expression, okay, and of course, we know what sigma top is and we know what is sigma net, of course, we discussed that, correct, okay. Now, if I know the charge diagram, okay, first I am trying to draw the charge diagram. So, this is your charge, this is your x, correct. So, I have given you the charge diagram, which is there is a plus NDD, there is a negative sigma top. This negative sigma top is actually higher in magnitude than plus q NDD. Then this is D. At this you have a plus sigma net, and very close to the interface you have minus q and s. Now, how will you draw the electric field diagram? Correct. So, I have to draw the electric field diagram on the same scale essentially, okay. Now, how will you draw the electric field diagram? The derivative of the electric field, is the charge by Poisson ratio. Field, okay, the derivative of the electric field with respect to position is the charge, okay. That also reminds me to tell you that the polarization that we have been talking about, okay, the polarization we have been talking about is essentially charge, So, the charge by epsilon is actually the field here, because it is a 2-dimensional we are talking about, it is not a 3-dimensional scenario. So, we are talking about a 2-dimensional scenario. So, it is the field is essentially the polarization by charge. Nevertheless, here how will I talk about a field? So, you can see that there is a net actually negative charge here, because I told you that sigma top negative sigma top is actually more than plus sigma ND. So, this is a net negative here, and this quantity is overall positive. So, if there is a negative here and there is a positive here and nothing in between, then there is an electric field. Which direction will be the electric field? The way to think of the electric field is that if you have a unit positive charge, it will try to move in this direction, correct. So which means the field is negative in x, okay, because the unit positive charge will move in this direction. The field is negative in this direction and the field is constant in this space between the in the layer D. The field is constant because there is a positive charge at the bottom, there is a negative charge at the top, in between there is nothing. So it is like a dipole, and so there is an electric field which is constant. The constant electric field, okay, the constant electric field is negative in direction. So I can say this is negative, this is the electric field, and the value, and this is D by the way, the value of the electric field is something F1 for instance, maybe F1, okay, it is okay, I will just call it F1, okay, it is the electric field which is here. And because this is step and this is also step, so essentially what happens is that there is a step function here. So the field will increase, just come to this value, go here, another step and then decrease, there is no field beyond that point. The 2DG density or this mobile electron density is very close to the interface, so it is here, so it actually goes like that, but that is okay. So this is the electric field, okay. So this is the electric field, and the magnitude of the electric field is nothing but the charge by the epsilon. In this case the charge is the net charge, this, which is equal to the other charge, right. So what I am trying to say is that sigma net minus q n s, okay, divided by epsilon naught epsilon s, where epsilon s is the, it is 8.9, it is basically gallium nitride epsilon, the dielectric constant, very close to also Elgin dielectric constant, you can take it as 9 or 8.9. So this quantity is actually the field here, the field there is actually that quantity. So this F1 is this quantity, okay, because the charge by epsilon, this is 2 dimensional, alright. So now how will you draw the energy band diagram? If you know the field here, so if you have a constant field, the derivative of the energy band diagram has to be constant, the derivative of the energy band or the potential has to be constant, because the field is the derivative, of the potential. So what is that function, mathematical function whose derivative will give you a straight line like this, I mean a constant value like this? It is a linearly varying line or a slope, you know, if you have a function like that slope, if you take a derivative of that you will get a straight line, constant line, right, which means the potential has to be now constant. So I will come to that last slide or discussion of this lecture then, which is if I try to draw the energy band, okay, if I try to draw the energy band, so this is 0, this is D, I know the electric field is negative. Remember, if the electric field is negative in this direction, then electron will roll downhill this way, electron will move in this direction, which means the energy band diagram has to be in this direction. This is your maybe I will use a different color, I will use the red color maybe. So this is your conduction band, maybe this is your valence band, correct. This is a conduction band, this is a valence band. Why is it in this shape? Because an electron will roll downhill like that, which means the field is in this direction, which is what precisely I told in the last slide here, right. So this is your, and this is your the energy band gap, right, of your Elgin, this is your Elgin on the top, okay, and assume that this is your Fermi level, is okay, this is your Fermi level, okay. Now there is GaN here. Now this band gap is large, say 4.2 electron volt, but this band gap is 3.4 electron volt, which means at the interface there will be discontinuity, correct, there will be discontinuity because GaN has a smaller band gap. The GaN band gap could be something like this. So this is your 3.4. At interface there is a discontinuity, so it will come like that, it will go like that, it will go like that. So the thing to note here is that at this interface it will look like, and this is your Fermi level. Why did it happen? Because I told you there is a mobile electron gas that has formed, correct, and that mobile electron gas is here, it is like a quantum well, it is a quantum well. What is a quantum well? In class 10+2 or in our undergrad first year we might have studied about it. Quantum well is basically when you have potential surrounded by higher potential, so that it's like a well, electrons cannot go in this direction. So this direction is, by the way, the z axis or the z direction, which is the growth direction. You are basically growing the crystal in this direction. Remember, this is your Elgin and this is your GaN. So, you are growing the material in this direction. So, this is precisely the direction, the growth direction. So, the electrons that are trapped in this quantum well, cannot move in the z direction because it is a barrier. So, you can see that it is like a well where you have something like that. Okay. The Fermi level, maybe I will use the black color for Fermi level. So, this is a Fermi level. So, the electrons that are there, they cannot move in this direction because it is trapped in the well. So, it is a barrier here. The barrier is given by delta E c, which is your discontinuity on the conduction band between L GaN and GaN. On the other side there is GaN, of course. So, you cannot move the electron in the z direction, they can only move in the x and y plane. They can only move in 2 dimension. The 2 dimension is basically, if you look at this initial figure here, then this electron gas that exists here, they can move in this direction and they can move in this direction. It is like a xy plane, they cannot move in this direction, cannot. Okay, they cannot move in this direction. So, that is why they are confined in the 2 dimension and we call them 2 dimensional electron gas, because they can only move in the x and y plane, not in the z direction. Okay. So, they are 2 dimensional electron gas, and this entire thing we are talking about areal density and things. So, the charge density of this also will be expressed in number of electron or coulomb per centimeter square. Remember, polarization is also expressed in coulomb per centimeter square because it is an areal density, areal as in the area per unit area, it is not a volume density. Okay. So, essentially the volume density of polarization actually vanishes, it becomes 0. Like if you take a derivative of the polarization of this abrupt polarization, it is actually 0, but the polarization itself does not vanish. At the interface you have a discontinuity in the polarization. That discontinuity in the polarization and the discontinuity in the energy band gap gives rise to this notch. This gives rise to the notch, and just because there is a notch does not mean there will be electron gas. In this case, the mobile electron gases are literally coming from the ionized surface states. They have donated the electrons. Okay. They have donated the electrons, they have accumulated here. The fact that there is polarization, it is the polarization has assisted in the formation of the 2D electron gas. Polarization has assisted. Okay. Polarization is not the source of the 2D electron gas, please remember that. Polarization is not the source is still the surface donor ions or maybe remote impurities or background impurities, whatever it be. The source of electron is not polarization. Polarization has assisted in the formation of your 2 dimensional electron gas. Okay. Polarization has assisted, but again without polarization you will not get the 2D electron gas even if you have surface donor. You see this field here. Okay. So, the overall charge neutrality, to maintain overall charge neutrality, the system will pull in electron from remote impurities, defects, dangling bonds, what have you. It will pull in electrons and form the quantum well with the 2D electron gas density such that the total charge neutrality is maintained. If you do not have polarization in a material, so for instance I told you that L GaN can also have a different phase which is a cubic phase. In cubic phase L GaN does not have polarization. In that case you will not get the 2D electron gas because there is no polarization. We do not worry about the charge neutrality as much as we have talked here. So, the 2D electron gas does not have to form. Okay. So, if you take just a cubic phase or a non-polar plane of L GaN, for instance M plane, A plane, you will not get a 2D electron gas unless you modulation dope it. Okay. So, this is the beauty of your polarization which has assisted in the formation of 2D electron gas. Okay. So, with that we will conclude lecture 7 here. Okay. So, today is we are concluding lecture 7 here, where we discussed about the formation of electron gas, and also we talked about in little bit more details about piezoelectric polarization and also how the heterostructure band diagram is drawn, the charge diagram, the field diagram, etc. So, in the lecture 8, the next lecture, we will talk about a little bit more about this L GaN Hem structure. In the context of the 2 dimensional electron gas that has formed, we shall discuss about some of the properties of this 2D electron gas and why it helps in forming a transistor. Before we talk about an RF transistor, we need to understand how the basic L GaN transistor works. Okay. So, with that we will conclude this lecture and we will see you again in lecture 8. Thank you.